Welcome to the series on the playlist of videos on essential concepts of probability for data science. This is Hemakumar Kasla, and I wish to introduce you to the basic properties on probability and other rules and definitions in this session. It is essential that you have gone through the previous two videos on basic concepts and definitions on probability and conditional probability before watching this session. Let's get into the session. What's the real need to understand the properties of probability, rules, and definitions? Given the complexity of evaluating probabilities using relative frequency approach for not equally likely outcomes cases especially, one can imagine that the effort required in evaluating probabilities for complex events can be huge. For example, like A union B intersection C or complement of A intersection B, where A, B, and C are individual events. Evaluating the probabilities in such cases by direct application of the relative frequency approach can be quite cumbersome. Fortunately, the probabilities of complex events can be derived from the probabilities of less complex events. In other words, from simpler events. In order to do that, one needs to understand the various properties of probability, rules, and definitions around it. The probabilities of complex events can be derived by applying the properties of probability, rules, and definitions on the known or derivable less complex event probabilities. And hence, let's start and look into some of the basic properties of probability to begin with. Basic property number 1 is, for any event E, probability of E is greater than or equal to 0 and less than or equal to 1. In the relative frequency approach with n trials, where n is a very large number, probability of E is defined as the ratio of number of occurrences of outcomes in E to the total number of the trials. Number of occurrences of outcomes in E cannot be a negative number, and hence the probability of E has to be a number greater than or equal to 0. And similarly, number of occurrences of outcomes in E cannot exceed the total number of the trials, and hence the probability of E has to be a number that is less than or equal to 1. Hence, number of occurrences of outcomes in E has to be anywhere between 0 and total number of the trials. And thus, probability of E has to be a value that is greater than or equal to 0 and less than or equal to 1. Basic property number 2. Probability of S equals 1 where event S is the entire sample space. Because the probability of any event is the proportion of the time an outcome in an event occurs in the long run, and because the sample space S consists of all possible outcomes for a chance experiment, an outcome in any given trial is an element in S. Hence, probability of S, which is the number of occurrences of outcomes in S divided by the total number of the trials, equals n divided by n, which is 1. Basic property number 3. If two events E and F are disjoint, then probability of E or F equals probability of E plus probability of F. Disjoint events are those that do not share any outcomes from the sample space common between them, meaning none of the outcomes in event E is present in event F and vice versa. That being the case, the definition of probability involving two disjoint events E and F using the relative frequency approach shall be probability of E or F equals the number of outcomes of E in n trials plus the number of outcomes of F in n trials divided by the total number of trials n, with n being a very large number. Note, since there are no outcomes that are common between the two events in the above ratio, there is no subtraction in the numerator of the above expression. Hence, probability of E or F equals number of outcomes of E in n trials divided by total number of trials n plus the number of outcomes of F in n trials divided by the total number of trials n. Since the ratios in the right hand side of the above expression are the probabilities of event E and event F respectively, probability of E or F equals probability of E plus probability of F. Note, since the simple events are essentially disjoint, this basic property applies to the simple events as is. For disjoint events E and F, probability of E or F, which equals probability of E union F, that equals probability of E plus probability of F, is called the addition rule for disjoint events. This rule can be generalized for more than two disjoint events as well, as in probability of E1 or E2 and so on until En equals probability of E1 union E2 and so on until En, which in turn equals probability of E1 plus probability of E2 and so on until probability of En. Basic property number 4. For any event E, probability of E plus probability of not E equals 1. Since probability of E and probability of not E are disjoint, probability of E plus probability of not E equals probability of E plus not E. Since event E plus not of event E equals the sample space S, probability of E plus probability of not E equals the probability of the sample space PS. Since probability of S equals 1, probability of E plus probability of not E, which is probability of S, equals 1. From probability of E plus probability of not E equals 1, we get probability of E equals 1 minus probability of not E, and probability of not E equals 1 minus probability of E. The above two equations are quite useful when one of the two probabilities are not straightforward to evaluate. Probability of E can be derived from probability of not E when probability of E is not straightforward to evaluate, and vice versa. Having discussed the basic properties of probability, let's look into further definitions and advanced rules on probability. Independent events. Events E and F are defined independent if probability of E given F equals probability of E, and similarly probability of F given E equals probability of F. What this means is the relative frequency of event E occurring given event F is the same as the relative frequency of event E given the whole sample space S. And the same applies swapping events E and F in the above statement. In other words, the relative frequency of event E occurring amongst the occurrences of event F is the same as the relative frequency of event E given the whole sample space S. And the same applies swapping the events E and F in the above statement. Events E and F do not influence each other, meaning occurrence of one of the events does not alter the relative frequency of the other. There are no special concurrences or dependencies between event E and event F. There is no special association between events E and F in the chance experiments. Events E and F are independent of each other. Multiplication rule. For independent events E and F, we learned that probability of E given F equals probability of E. Expanding probability of E given F, we get probability of E intersection F divided by probability of F equals probability of E. Thus, probability of E intersection F equals probability of E multiplied by probability of F. The above equation is called the multiplication rule. Multiplication rule states that for independent events E and F, the probability of E and F, which is probability of E intersection F, is equal to the product of their individual probabilities. Conceptual understanding of the multiplication rule. Probability of E intersection F is the probability of concurrent occurrences of event E and event F. Concurrent occurrences of event E and event F in probability of E intersection F can be rephrased as the product of relative frequency of occurrence of event E multiplied by the relative frequency of occurrence of event F given event E. Translating the above statements into an equation, we get probability of E intersection F equals probability of E multiplied by probability of F given E. Since probability of F given E equals probability of F for independent events, we get probability of E intersection F equals probability of E multiplied by probability of F. Multiplication rule for multiple independent events. The multiplication rule can be extended to multiple independent events E1, E2 and so on until En as well, as in probability of E1 intersection E2 and so on until En equals probability of E1 multiplied by probability of E2 and so on until probability of En. Since the events E1 to En are independent of one another, their individual conditional probabilities, probability of Ei given Ej, are replaced with their respective independent probabilities, probability of Ei, in the above multiple event multiplication rule. General addition rule for two events. It is already discussed that for disjoint events, probability of E union F equals probability of E plus probability of F. However, for non-disjoint events, the above equation requires an adaptation. Since there are outcomes that are common between event E and F, above equation is modified as follows for non-disjoint events. That is, probability of E union F equals probability of E plus probability of F minus probability of E intersection F. In the above general addition rule, since probability of E and probability of F include the probability of the common outcomes, probability of E intersection F in each of them, in other words, probability of E intersection F is included or added 2 times in probability of E plus probability of F, and one subtraction of probability of E intersection F is accounted in the above equation. Let's look into the mathematical derivation of the general addition rule for the sake of completeness. In order to derive the general addition rule for non-disjoint events, let's expand probability of E union F as follows. Probability of E union F equals probability of OE union OC union OF, where OC is an event constituting the common outcomes between E and F, OE is an event constituting the outcomes of event E minus those that are part of OC, and OF is an event constituting the outcomes of event F minus those that are part of OC. Since OE, OC and OF are disjoint, the above equation, for the sake of understanding and further derivation, can be written as probability of E union F equals probability of OE plus OC plus OF. Adding and subtracting OC in RHS of the above equation, we get probability of E union F equals probability of OE plus OC plus OC minus 2OC plus OF plus OC. Since OE plus OC equals event E and OC minus 2OC equals minus OC and OF plus OC equals event F, this equation can be rewritten as probability of E union F equals probability of E minus OC plus F. Right hand side in the above equation can be replaced with their respective individual probabilities and can be rewritten as probability of E union F equals probability of E minus probability of OC plus probability of F. Since event OC equals event E intersection F, the equation above can be written as probability of E union F equals probability of E plus probability of F minus probability of E intersection F. Thus we arrive at the above general addition rule. Probability of E union F equals probability of E plus probability of F minus probability of E intersection F is called the general addition rule for two events because it applies not only to non-disjoint events but also to disjoint events. Since probability of E intersection F equals 0 for disjoint events, the addition rule for disjoint events becomes probability of E union F equals probability of E plus probability of F. While the addition rule for the non-disjoint events stays as probability of E union F equals probability of E plus probability of F minus probability of E intersection F. General multiplication rule. Derived from the conditional probability equation, probability of E given F equals probability of E intersection F divided by probability of F is the general multiplication rule for two events, which is probability of E intersection F equals probability of E given F multiplied by probability of F. The above equation shall equally take the following form: probability of E intersection F equals probability of F given E multiplied by probability of E. Thus the general multiplication rule for two events is probability of E intersection F equals probability of E given F multiplied by probability of F, and also probability of F given E multiplied by probability of E. Probability of E intersection F equals probability of E given F multiplied by probability of F is the general form of the multiplication rule for both independent and non-independent events. While the equation is used as is for the non-independent events, probability of E given F in the above equation is replaced by probability of E for independent events. And thus, for independent events, probability of E intersection F equals probability of E multiplied by probability of F. While the multiplication rule probability of E intersection F equals probability of E given F multiplied by probability of F is useful to evaluate the unknown probability of E intersection F when probability of E given F is known, the other form probability of E given F equals probability of E intersection F divided by probability of F is useful to evaluate the unknown conditional probability of E given F when probability of E intersection F is known. Law of total probability. Let's try and understand the context for law of total probability via an example. Let's assume that a shop sells two brands of TVs, brand X and brand Y. Let Bx be the event that a brand X TV is purchased and By be the event that a brand Y TV is purchased. Assume that probability of Bx is known and that equals 0.55, and similarly assume that probability of By is known and that equals 0.45. Note that Bx and By are disjoint events whose probabilities are known and sum of their probabilities equal 1. That is, total probability equals 1. Let E be the event that an extended warranty is purchased for each of the TV being bought, and assume that probability of E is not known. However, probability of E given Bx is known and that equals 0.2, and probability of E given By is also known and that equals 0.25. What is the value of probability of E? Is it possible to derive probability of E given the values of the above individual and conditional probabilities? The answer is yes, and the law of total probability provides the solution. Law of total probability. Let's get into the concept of law of total probability. Let sample space S represent the outcomes of a given chance experiment. Let B1, B2, B3 and B4 be 4 disjoint events whose individual probabilities are known and sum of their individual probabilities sum up to 1. That is, the total probability equals 1. Let event E as shown shares its outcomes across B1, B2, B3 and B4 with an unknown probability PE. The law of total probability enables the derivation of probability of E as in probability of E equals probability of E intersection B1 plus probability of E intersection B2 plus probability of E intersection B3 plus probability of E intersection B4, provided all 4 probabilities of E intersection Bi are known. If probability of E intersection Bi are not known, but the individual conditional probabilities for event E, that is, probability of E given B1, probability of E given B2, probability of E given B3 and probability of E given B4 are known, then the law of total probability can use these conditional probabilities and evaluate probability of E as probability of E equals probability of E given B1 multiplied by probability of B1 plus probability of E given B2 multiplied by probability of B2 plus probability of E given B3 multiplied by probability of B3 plus probability of E given B4 multiplied by probability of B4. And hence, general expression for law of total probability can then be written as probability of E equals probability of E given B1 multiplied by probability of B1 plus probability of E given B2 multiplied by probability of B2 and so on until probability of E given Bn multiplied by probability of Bn. Going back to the example that we started with for understanding the law of total probability, the expression for evaluating the probability of the event E that the extended warranty is purchased can be written as probability of E equals probability of E given Bx multiplied by probability of Bx plus probability of E given By multiplied by probability of By. Substituting the values for probabilities in the right hand side of the above expression, we arrive at the probability of E as 0.2 multiplied by 0.55 plus 0.25 multiplied by 0.45, which equals 0.2225. That brings us to the end of the session on understanding the basic properties and other rules and definitions on probability. Please share your questions or remarks if any, and I'll try and respond back as soon as possible. Thank you, and see you with the next session on the playlist of videos on the essential concepts of probability for data science. Bye until then.